Moving into part 2 here, section 4, we're just going to look at a few more examples of doing those inverse Laplace transformations. Before we do some examples, just a quick theorem. This theorem's the same theorem basically that we had for the Laplace transformation. It just works the other way around. It's that linearity theorem. So if we have the inverse of two Laplace transformations added together, then instead of doing it like this, we could split it up and just do the Laplace inverse of the first transformation plus the Laplace inverse of the second. Okay, great. And then this one says the same thing as part 2 of the last one. So if you have the inverse of a constant times a Laplace transformation, then you can take that constant out of the inverse. Okay, cool. So using that, we're going to do some examples here. I need the book, so let me pull up the book here real quick. Alright, I got the book pulled up, ready to go. Remember, this is the table that we're using to do these inverse Laplace transformations. So let me write out the example that we want to do here. So find the following. So we want to do the inverse Laplace transformation of, it's going to be kind of a big one here, 5 over s minus 6 minus 6s over s squared plus 9 plus 3 over 2s squared plus 8s plus 10. Okay, great. Yeah, so just using the theorem that we have up top here, we have three things that are all added together, so we're going to split that all up. We also have these constants up top that we can pull out if we need to. So let's go ahead and do all that. We're going to rewrite all this. This first one here, I'm going to pull out the 5, and then we're going to have a Laplace transformation, inverse Laplace transformation of just 1 over the s minus 6. Okay, doing the same thing for the next one. So we're going to pull out a negative 6, inverse Laplace transform of what's left, s over the s squared plus 9. Plus we're going to pull out the 3, again, inverse Laplace. We're going to have the 1 over 2s squared plus 8s plus 10. Okay, so now that we've done all that, now we need to go to the table and figure out what all of these are. So 1 over s minus 6, that looks like it's going to be an e to the a t, where the a is 6, so e to the 6t there. This one, s over s squared plus 9, s over s squared plus something, that looks like a cosine one, where my b is going to be 3 in this case, so cosine of 3t for that one. This one's not going to match any of them because we're going to have to do that same technique that we did before, where we're going to need to do a completing the square. So let's go ahead and start writing out some of these. Remember that this one was an e to the 6t minus 6. This one was a cosine of 3t. Okay, plus, I'm going to get a little bit fancy here with this one because when you do completing the square, this coefficient in front of the squared term has to be a 1. So I'm going to factor out a 1/2 out of the Laplace inverse. All right, and we're also going to go ahead and do the completing the square at the same time. So this is going to be now just an s squared when we factor the 1/2 out, plus this term's just going to be a 4s, plus this is going to be a 5. But let's go ahead and do the completing the square. So we have a 4s here. We're going to take half of that and square it, which is positive 4. Remember that this 10 has now turned into a 5 because we factored the 1/2 out. But if we're going to add 4 into this, we also have to subtract 4 into it. All right, so copying everything we got down. Ooh, sorry. plus the 3 halves. Okay, so now still doing the inverse Laplace transform. We're going to change this up now by factoring the first 3 terms here. That would factor in an s plus 2 all squared. And then we're going to have plus 5 minus 4, which is a plus 1. Oops, that's supposed to go down there. Okay, now let's go to that table to see what this looks like. 1 over s plus something squared, all plus 1. In our table, it looks like it's got to be one of these down here. We do not have the s minus a up top, right? We just have a constant up top. So it's going to have to be this one, where our b is 1, because we have a 1 here, and a 1 squared, or just a 1 there. We don't have s minus a, right? We have s plus 2, so our a is going to be negative 2 to get it to fit into here. Okay, so this was the e to the at sine bt, so go ahead and write it out. Still have the 5e to the 6t. T. Nope, not there. Jeez, sorry. Minus the 6 cosine 3t. We're going to have that plus 3 halves. And now this inverse Laplace transform, remember, was e to the negative 2t, and then it's sine of just 1t. And that's it. So that is going to be the inverse Laplace transformation of this awful thing right here. Or another way to think about it is if you did the Laplace transformation of this, you would get this up top. All right, maybe one more. This one is just a trick that you're going to have to get used to when doing these inverse Laplace transformations. So here we have 5 over s plus 2 all to the 4th. Okay, so it's just one term here, so let's go ahead and look at the table in the book to see which one this matches. We have a constant up top, and then an s plus a constant to the 4th power in the bottom. It looks like it's going to have to be this one here. Okay, so we have this e to the at, t to the n. The power in the denominators was going to decide the n for us, right? It was to the 4th power, which means that our n is going to be 3. Instead of s minus a on the bottom, we had s plus 2, so our a is going to be negative 2 again. So it's going to be e to the negative 2t, and then t to the power of 3. The problem, though, is that if I had a 3 factorial up top, 3 factorial is 3 times 2 times 1, which is 6, but we don't have a 6 in the numerator, we have a 5. So we need to make there to be a 6 in the numerator, that way it's the inverse Laplace transformation. And to do that, we're going to pull that 5 out of there, and we're going to force it to have a 6 up top by also factoring out a 1/6. So if I factor out a 1/6 from the inverse here, that's going to leave me with a 6 in the numerator, and then that s plus 2 to the 4th in the denominator. Now we can just go ahead and rewrite it as the inverse Laplace transformation. This is the 3 factorial up top, the 3 plus 1 exponent on the bottom, and our a is negative 2. So this is going to change to be e to the negative 2t and then t cubed. Okay. One last thing I want to show you before we end section 4 and get into the most important section here, section 5, and that is sometimes you're going to have to use the method of partial fractions. So let's just go ahead and jump into an example, because I hope all of you remember how to do partial fractions. So we're going to do, this is our example here, the inverse transformation of 7s minus 1 divided by s plus 1 s plus 2, s minus 3. Oops. Oh no. There he goes. Oh, Jesus. Alright, you're just going to have to suffer with this not curly bracket there. Okay, great. So if you ever see something like this, this is also not going to match any of the ones in the table. So what we can do is we can break this up into 3 separate fractions, all with these denominators using the partial fraction decomposition. So let's go ahead and do that. Remember to do that. You want to rewrite it down here. I'm just going to write down the inside part, the 7s minus 1 over the s plus 1, the s plus 2, the s minus 3. Okay. Why is my 7s over there? Sorry about that. should be up here, 7s minus 1. Okay, and now remember the partial fraction decomposition with this. We have all linear terms in the denominator. They're all to the power 1. So we're going to have an a over the s plus 1. Plus we're going to have a b over the s plus 2. Plus we're going to have a c over the s minus 3. Okay, I'm gonna insert the secret code at this point. I'm just going to type it out. So the secret code is this. Cool. So that's that extra credit secret code. Awesome. Keeping it going here. Remember what you want to do now is you want to multiply both sides by the denominator. So we're going to get a 7s minus 1 on the left. And then all this is going to be kind of ugly looking. We're going to get the s plus 2 times the s minus 3 multiplied on the a. Plus for the b, we're going to have the s plus 1 and the s minus 3. Plus the c, we're going to have the s plus 1 and the s plus 2. All right, so that's just multiplying both sides by this common denominator. S plus 1, s plus 2, s minus 3. All right, so you could multiply all this stuff out and do it that way. Remember there's another method that you can do where you just plug in different values that make stuff disappear. So let's try plugging in s to be negative 2. Because I noticed if I plug in negative 2, this parentheses is going to go to 0. This parentheses over here is going to go to 0. All right, so negative 2 in for the s here. 7 times negative 2 is negative 14. Minus the 1 is negative 15. That's on the left. This term is all just 0. Plugging negative 2 into this term, I get a negative 1 and a negative 5, which is positive 5 onto the b. And then this term over here is also going to be 0. Looks like our b is going to be negative 3. Let's try another value that makes stuff disappear. So positive 3 would make that parentheses and this parentheses disappear. If I plug positive 3 into all three sides, I'm going to get 20 on the left, 0, 0. If I plug 3 over here, I get 4 times 5, which is 20c, which says that my c has to be 1. Last thing that we could try would be a negative 1 to make this parentheses and this parentheses 0. So just plugging in negative 1 to all three sides, we get negative 8 on the left. We get, looks like a negative 4a, and then everything else is 0, so a has to be 2. All right, so now rewriting out that partial fraction decomposition, and we'll go ahead and write it into the Laplace inverse. So don't forget the whole point is that we're trying to take the Laplace inverse of this thing, but we've now broken this thing up into 3 separate fractions. So it's a over the s plus 1, so a was 2, so 2 over the s plus 1, plus the b, which is negative 3 over s plus 2, plus the c, which was 1 over the s minus 3. Okay, and then of course from here there's 3 things added together, so we would do the Laplace inverse of all 3 of these separately. Just going back over to the table in the book, that looks like these are all e to the at's. So we're going to pull the constant out from the tops, and it's the opposite of the constant for the a down here. So the first one, I'm going to take that 2 out of there. This is really going to be a negative 1, so it's going to be e to the negative t. For the next one, I'm going to take the negative 3 out. I have a positive 2, which means that's really a negative 2t. Plus, there's no constant, so just the 1 e to the, that one's going to be a, oops, I put negative, but it should be a positive 3t there. And then that's it. So that's going to be the Laplace transformation. So just keep in mind that you may need to do partial fraction decomposition to find these inverses.